Alright, so it looks like this is an impulse problem. We have a ball in contact with the floor for 0.025 seconds, and we want to know the average force exerted during that time interval. So, alright, let's consider this motion. I'm going to establish a sign convention that up is positive and down is negative. Okay, so this ball starts out at a height of 2.1 meters and hits the floor. Okay, so that'll be part one, where the ball is in free fall, and part one will end the instant before the ball hits the floor. Part two will be the time during which the ball is in contact with the floor. Now, with part two, we can't analyze that as an F equals ma or a motion with constant acceleration, because during the time that the ball is in contact with the floor, the acceleration is not constant. The ball is being deformed, and it kind of acts like a spring, and it's very complicated. So we can't use our equations of motion with constant acceleration for that, but we don't need to. Right? And then the ball then leaves the floor. So part two begins the instant the ball makes contact with the floor, and part two ends the instant the ball leaves the floor. So in part three, the ball goes back up to a maximum height of 1.7 meters. Okay? So, let's see. So what we need in part two is we want to know what is the magnitude and direction of the average force exerted by the floor on the ball during that time interval. So if we wanted to find that force, we could try F equals ma, but you can't do that because we have no idea what the acceleration is. You can't really get that. Well, you can, but an easier way to say it is that we can use delta p is equal to F delta t. Right. I suppose I could, if I wanted to, I could solve for the acceleration being v minus v naught over delta t, right, and say F is equal to this. But this equation is the same thing, right? So let's just solve for this average force. We'll say that the average force is equal to the change in momentum over the change in time. So that's mv minus mv naught over t. So what we need, we've got t, we've got m. What we need is the initial velocity the instant before it hits the floor, and the final velocity the instant it leaves the floor. So let's consider part one of this real quick. So for part one, we know we know that it goes through a displacement, a vertical displacement of negative 2.1. Remember this from chapter 2, that down is negative in this problem, and so the delta y displacement has to be negative 2.1. It has a magnitude and a direction. We're told that it's dropped from rest, and we know the acceleration is negative 9.8 meters per second squared. So let me use the equation that doesn't have time in it to find final velocity. So I get v1 squared is equal to 0 plus this, right? And notice the minus signs work out. And so v1 is plus or minus 6.416 meters per second. We'll take the negative value of that since it's going down. Okay, so there's v1, which is the initial velocity for part 2. Okay, which we can plug in right up here. Now let's do part 3, which is the upward motion. So it goes up 1.7 meters, reaches a maximum height, so the final velocity is 0. Still has a negative acceleration, of course, because it's in free fall. Okay, so let's see, v3 squared Alright, so I get 0 is equal to v0 3 squared plus... Okay, notice that the signs, again, are going to work out. I get v0 is plus or minus 5 5.772, and so in this case I'm going to take the positive value because I know that V0 is directed upwards. Okay, so that V0 for part 3 is the final velocity for part 2, so I'm going to use that up here. Alright, so for part 2 then, the force is equal to mv minus mv0 over delta t. So that's the final velocity for part 2 is the initial velocity for part 3. And the initial velocity for part 2 is the final velocity for part 1. I'm going to divide that by my delta t, which is 0.025. Notice that I got a minus sign here and a minus sign here, so that's going to be added together. And I end up with 4.266 over 0.025, which gives me a force of 170 newtons. And it's positive 170 newtons, which, given my sign convention here, means that it's pointing up. So there's the magnitude and direction of the average force exerted on the ball by the floor.